Summary. In this chapter we looked at the issue of replication. Replication can serve several purposes. High availability, keeping the system running, even when one machine or several machines, or an entire data center goes down. Disconnected operation, allowing an application to continue working when there is a network interruption. Latency, placing data geographically close to users, so that users can interact with it faster. Scalability, being able to handle a higher volume of reads than a single machine could handle, by performing reads on replicas despite being a simple goal, keeping a copy of the same data on several machines. Replication turns out to be a remarkably tricky problem. It requires carefully thinking about concurrency and about all the things that can go wrong, and dealing with the consequences of those faults. At a minimum, we need to deal with unavailable nodes and network interruptions, and that's not even considering the more insidious kinds of fault, such as silent data corruption due to software bugs. We discussed three main approaches to replication. Single leader replication. Clients send all writes to a single node, the leader, which sends a stream of data change events to the other replica's followers. Reads can be performed on any replica, but reads from followers might be stale. Multi-leader replication. Clients send each write to one of several leader nodes, any of which can accept writes. The leaders send streams of data change events to each other and to any follower nodes. Leaderless replication. Clients send each write to several nodes and read from several nodes in parallel in order to detect and correct nodes with stale data. Each approach has advantages and disadvantages. Single leader replication is popular because it is fairly easy to understand, and there is no conflict resolution to worry about. Multi-leader and leaderless replication can be more robust in the presence of faulty nodes, network interruptions, and latency spikes at the cost of being harder to reason about and providing only very weak consistency guarantees. Replication can be synchronous or asynchronous, which has a profound effect on the system behavior when there is a fault. Although asynchronous replication can be fast when the system is running smoothly, it's important to figure out what happens when replication lag increases and servers fail. If a leader fails and you promote an asynchronously updated follower to be the new leader, recently committed data may be lost. We looked at some strange effects that can be caused by replication lag, and we discussed a few consistency models, which are helpful for deciding how an application should behave under replication lag. Read after write consistency. Users should always see data that they submitted themselves. Monotonic reads after users have seen the data at one point in time. They shouldn't later see the data from some earlier point in time. Consistent prefix reads. Users should see the data in a state that makes causal sense. For example, seeing a question and its reply in the correct order. Finally, we discussed the concurrency issues that are inherent in multi-leader and leaderless replication approaches. Because they allow multiple writes to happen concurrently, conflicts may occur. We examined an algorithm that a database might use to determine whether one operation happened before another, or whether they happened concurrently. We also touched on methods for resolving conflicts by merging together concurrent updates. In the next chapter we will continue looking at data that is distributed across multiple machines through the counterpart of replication, splitting a large dataset into partitions. Bruce G. Lindsay, Patricia Griffiths, Sellinger, C. Galtieri, et al. Notes on Distributed Databases. IBM Research. Research Report RJ 2571 33471, July 1979. Oracle Active Data Guard Real-Time Data Protection and Availability. Oracle White Paper, June 2013. Always on Availability Groups in SQL Server Books Online. Microsoft, 2012. Jen Rao. Intercluster Replication for Apache Kafka at ApacheCon North America, February 2013. Highly Available Queues in RabbitMQ Server Documentation, Pivotal Software, Inc., 2014. Robert Van Rennes and Fred B. Schneider. Chain Replication for Supporting High Throughput and Availability at 6th Usenix Symposium on Operating System Design and Implementation OSTI, December 2004. Percona Extrabacup Documentation, Percona LLC, 2014. John Hugg, All In with Determinism for Performance and Testing in Distributed Systems, at Strange Loop, September 2015. Yoshwar Sharma, Philippe Adju, Petchanang, et al. Wormhole, Reliable PubSub to Support Geo-Replicated Internet Services, at 12th Usenix Symposium on Networked Systems Design and Implementation in SDI, May 2015. Oracle Golden Gate 12c, Real-Time Access to Real-Time Information, Oracle White Paper, October 2013. Douglas B. Terry. Replicated Data Consistency Explained Through Baseball, Microsoft Research, Technical Report MSRTR 2011-137, October 2011. Tungsten Replicator, Continuant, Inc., 2014. BDR 0.10.0 Documentation, the PostgreSQL Global Development Group, bdrproject.org, 2015. Mark Shapiro, Nuno Preguiça, Carlos Baquero, and Marek Zaworski. A comprehensive study of convergent and commutative replicated data types, INRIA Research Report No. 7506, January 2011. Benjamin Fournier, Thomas Gazignaire, and Anil Madhavapati, Mergeable Persistent Data Structures, at 26 Easternase Francophones, des Langages Applicatifs JFLA, January 2015. Joseph Blomstedt, Bringing Consistency to RIAC, at Ricken West, October 2012. Project Baltimore Wiki, github.com, 2013. Apache Cassandra 2.0 Documentation, DataStax, Inc., 2014. RIAC Enterprise, Multi-Data Center Replication. Technical White Paper, Basho Technologies, Inc., September 2014. Sean Crids, A Brief History of Time and RIAC at Ricken, October 2014. Partitioning, as discussed in this chapter, is a way of intentionally breaking a large database down into smaller ones. It has nothing to do with network partitions, net splits, a type of fault in the network between nodes. We will discuss such faults in Chapter 8. Chapter 6 Partitioning. Clearly, we must break away from the sequential and not limit the computers. We must state definitions and provide for priorities and descriptions of data. We must state relationships, not procedures. Grace Murray Hopper, Management and the Computer of the Future 1962. In Chapter 5 we discussed replication, that is, having multiple copies of the same data on different nodes. For very large datasets, or very high query throughput, that is not sufficient. We need to break the data up into partitions, also known as sharding. What we call a partition here is called a shard in MongoDB, Elasticsearch, and Solr Cloud. It's known as a region in HBase, a tablet in Bidable, a vnode in Cassandra and RIAC, and a vbucket in Couchbase. However, partitioning is the most established term, so we'll stick with that. Normally, partitions are defined in such a way that each piece of data, each record, row, or document belongs to exactly one partition. There are various ways of achieving this, which we discuss in depth in this chapter. In effect, each partition is a small database of its own, although the database may support operations that touch multiple partitions at the same time. The main reason for wanting to partition data is scalability. Different partitions can be placed on different nodes in a shared nothing cluster. See the introduction to Part Roman 2 for a definition of shared nothing. Thus, a large dataset can be distributed across many disks, and the query load can be distributed across many processors. For queries that operate on a single partition, each node can independently execute the queries for its own partition, so query throughput can be scaled by adding more nodes. Large, complex queries can potentially be parallelized across many nodes, although this gets significantly harder. Partition databases were pioneered in the 1980s by products such as Teradata and Tandem Nonstop SQL, and more recently rediscovered by NoSQL databases and Hadoop-based data warehouses. Some systems are designed for transactional workloads, and others for analytics. See transaction processing or analytics. On page 90, this difference affects how the system is tuned, but the fundamentals of partitioning apply to both kinds of workloads. In this chapter we will first look at different approaches for partitioning large datasets and observe how the indexing of data interacts with partitioning. We'll then talk about rebalancing, which is necessary if you want to add or remove nodes in your cluster. Finally, we'll get an overview of how databases route requests to the right partitions and execute queries. Partitioning and replication. Partitioning is usually combined with replication so that copies of each partition are stored on multiple nodes. This means that, even though each record belongs to exactly one partition, it may still be stored on several different nodes for fault tolerance. A node may store more than one partition. If a leader-follower replication model is used, the combination of partitioning and replication can look like Figure 6-1. Each partition's leader is assigned to one node, and its followers are assigned to other nodes. Each node may be the leader for some partitions, and a follower for other partitions. Everything we discussed in Chapter 5 about replication of databases applies equally to replication of partitions. The choice of partitioning scheme is mostly independent of the choice of replication scheme, so we will keep things simple and ignore replication in this chapter. Figure 6-1. Combining replication and partitioning. Each node acts as leader for some partitions and follower for other partitions.